All right. So we want to find the bar forces, not the whole system, just of the four that we've identified here. Now, we've talked about method of joints, we've talked about method of sections, we've talked about zero force members. Just doing method of section seems like the logical one to do, since we just want a few elements. I can't make a cut through this structure. I could, but it would have four unknowns. So I can't make a single cut that would capture all four. So we're going to think about that for a second. Do we have any zero force cases? Well, case one was two elements. That would be A and E, but they both have forces applied, so they're out. Case two are three elements collinear. I mean, two are collinear. That would be H and F and C. But H and F have forces applied. But if you look at C, it matches case two. So which of these three forces do I know? I'll know CG. So one of the required forces for the problem is right up. So I can just write the force in CG is 0, and I'll just make a note that I did that using my zero force member inspection.
Is BC and CD also 0, or is it?
Which ones?
BC and CD.
No, they're equal.
Oh, that's right.
We don't know what those are. In fact, we're going to find BC. Okay, so with this guy out of the way, I just have these three, and I think you can see that's going to be a classic section where if I cut the structure right down the middle here, I'm just going to release 1, 2, 3 unknowns. So now the question that we have to ask ourselves, do we want to work the left side or the right side?
Left side.
Yeah. I like the left side. Why?
Smaller.
They both work, by the way. And there's no tremendous advantage of the left side. But on the left side, if you look at the reaction at A, it's just a roller. So that's just one unknown. The right side, E, is a pin. And although it wouldn't be that challenging to find, you do have two unknowns. So since I'm going to choose the left-hand side, and I'm going to redraw that free body later, the first thing I want to do is find what I need for that left-hand side, which would be the reaction at A. So how do I find just the reaction at A? Looking at the whole structure. And I'm going to sum moments at E. So I'm going to assume right-hand rule, and I'm going to sum moments at E and make sure it's in equilibrium. Okay, all the loads are along the bottom chord of the structure. You can see how they're listed. They're all acting down. So about E, they're all going to create what kind of moment? Positive or negative? Positive. And these first three, 1 kip, 1 kip, 1 kip, all have the same magnitude. So I'll write 1 kip. But then I'm going to write the moment arm of each one. So the first one from E to there is 12 feet. The second one is 24 feet. The third one is 36 feet. So I'm just saving myself a little writing. That takes care of the moment of all these forces. I've still got a 500-pound force here, so that's half a kip. And what's its moment arm? The distance from E to A, which is 48, right? And then that's all being balanced by the reaction AY, which creates what kind of moment? Negative. And that has also a moment arm of 48. So we should be able to solve for AY. I think it's 2. But you want to check the numbers. Is it 2?
Yeah.
2,000.
Yeah,
Kips.
2 kips. They came out positive. So I'm done with that. I don't need to go over here and find EY and EX. That's not a surprising finding. If you look at all the sum of all the force, first of all, the force is symmetric about the center. The geometry is symmetric. So I've got a total of 4 kips acting down. It makes sense that half would be handled by A, the other half by E. So now I'm going to draw my free body diagram of this left-hand side here. So, this top one will be the force from B to C. This guy, the diagonal is from B to G. This one on the bottom is from G to H. In addition to that, I've got a applied force acting down here of 1 kip. Applied force here of 1/2 kip. And then I've got my AY reaction up, which is 2 kips. I think that's everything. I guess I can write some dimensions. This is 12. This is 16. I'll go ahead and put some lines here to indicate that those will go through G. Did I leave anything out? I think that's it. So just like our example problem, we can start applying moments if we can. So if you look at this one, BC, BG, where do they go through? They go through B. So that's a good place to sum moments, right? These two, BG, GH, go through G, so we'll do that. And then we're left with this guy here in the middle. And just like our example problem previously, it's the only, of the 3 unknowns, it's the only one with a Y component. So we're going to sum moments at B, some moments at G, some forces in the Y. And in each case, we're going to get one equation, one unknown, and I can write those in any order I want. Doesn't matter which one I do. I'll start with the moments first. So I'm going to sum moments at the top B. So I'm looking at the sum. I'm summing the moments about B. So BC and BG pass through B. So the only unknown will be GH. And GH is creating what kind of moment about B? Positive. So I have a positive moment created by the force GH. And what's the distance from B to that line of action? It's the height of the truss, or 16 feet. Who else creates moment about B? Does this 1 kip force here at H create moment? No, its line of action passes through B. So the only thing I have left are these 2 guys. Now, one is up and one is down. You could account for them separately, but you could also just sum those forces and get what? An equivalent force of 1.5 kips acting up. Right? And they're all along that same line of action. So I'm just going to use the 1.5 to save some time. So about B, this force creates what kind of moment about B?
A negative.
Negative. So I'll have a minus for my moment. My force is 1.5 kips. The moment arm, the distance between these is 12. So I should be able to find the force in GH. I don't know what that is off the top of my head. 1.125. 1.5 times 12 divided by 16.
1.125.
And that comes out positive. 1.125 kips positive. So that means that GH down here is in tension. Does that make sense? Well, here's my truss. All the forces are down. So is this structure going to bend into a happy face or a frowny face? Is it going to smile at you? I think so. So the bottom will stretch. Stretch is tension. And the top should go into compression. So we're probably going to find out, hopefully we'll find that BC is negative. And we'll find that out actually right now. So let's sum moments. At the second place we identified some forces that were concurrent. That's at G. So summing moments about G, the force here, yeah.
Can't we just sum the moments in the y direction and do the x direction? Not the moments, I mean, just the forces in the y and the x. And we don't have to sum moments again.
Well, if you sum forces in the y direction, you can get BG. If you sum forces in the x direction, well, after you get BG, you could do sum forces in the x. But that would include the answer BG. If BG is wrong, then you missed it. You could do that. And if you do it correctly, you'll get the same answer. I like the strategy where you don't bring along any previous answers if you don't need to. So by going to G, it eliminates BG and GF. I only have one thing, BC. And about G, that's going to create negative moment. Its moment arm will be the height, which is 16. And about G, what else do I have? I've got this force and this force. This is the equivalent one of the two. So I'll start here with this guy, H. About G, that's positive moment. So the force is 1 kip. The moment arm, G to H, is 12. And then I got the 1.5, which is creating negative moment. And its distance is 12 plus 12 is 24. So I should be able to solve for the force in BC. I don't know what that's going to be. 36, 24. What's 24 divided by 16? 1.5. So that comes out to be negative 1.5. So BC is negative, means compression. BC being in compression, we talked about that previously. That makes sense. And this kind of gravity loading, the bottom stretches, goes into tension, the top compresses. So now we're left with the only thing we don't have, which is BG. It's the only one with a Y component. You could sum forces in the X here too if you'd like, but you would bring in both your previous answers. Could be a source of error, maybe not. But again, I like this process. By summing forces in the Y, I don't bring back any of these unknowns. And I look at just the Y component. In this particular element here, it has a rise of 16 over a run of 12. So you divide everything by 4. You get a nice 3, 4, 5 triangle. The vertical component would be 4. And it's acting down. So I'd have 4 fists of BG. That's this guy down. Who else is down or up? 1 kip is down at H, and then I've got my equivalent force acting up of 1.5 kips. So I should be able to solve for BG, and that's going to end up being in tension. I don't know what that is. 0.625, I'm guessing. It should be 0.5 times 5 divided by 4. What'd you get?
0.65.
And that came out positive. So that diagonal force there would be in tension. That makes sense too. You might remember earlier in the course we talked about that under gravity loadings, if your diagonals kind of point towards the center, they're usually in tension. So any questions about this one? Okay, that's only took 15 minutes.